All right, so welcome. Some people may be joining. It's still only a few minutes after the official start time. Same thing as last week. If you were here, if you weren't here, we'll go over some of the things you can catch up on. But we'll be going till around 10:30, so about an hour and a half. We'll take some breaks here or there. Sometimes, doing a practice problem, I might say take a few minutes. Even myself, talking for an hour and a half, I need to catch my breath every so often. So we'll build in a break or two here or there. If you have a piece of paper on you, that's great, something to write on. There will be practice problems. I do put notes in these. I put notes in quotes because I will be posting these. I know for last week, I don't think they're up yet, but there is a video that was posted. So segue into my next point. If you missed last week, that is, you weren't here, people are on vacation, you weren't able to make it. I did post a video recording, and I'm recording right now as well, so I'll be posting that later today or tomorrow morning. I'll be posting a PDF of these slides, these little, what you should be able to see my iPad screen right now. I didn't post them from last week. I have them. I'll probably do it at some point during our meet today. So if you'd like to look over the notes that way, if you're someone like you have your notebook open right now and you're like, hey, I really like to stay organized. I'm a note person. That's great, but you certainly don't need to copy any notes. More so, what I would strongly recommend is, like I said, having something available, just so when I say, hey, try this problem, you're not taking a few minutes to look for a piece of paper. So have something out in front of you now. All right. So our agenda for today, I am switching something up. If you have a good memory, um, towards the end of last week, I said, we'll be covering equations and inequalities. I'm going to push that back till next week, so session 3. Today, we are going to be doing more polynomial stuff. We got a good amount done in session 1. I figured we'll just kind of make a connection and keep running with some more polynomial related things. Today, we're going to talk about factoring strategies and all that entails. So first, I guess this really just applies to people that were here last week, or maybe you weren't here last week and you tried to do it. Are there any delta math related questions? A, with signing up, like, hey, I can't even create an account. I didn't really get any issues with that, I don't think. Or B, I saw a few people wrote like, I wasn't sure how to type something. I didn't like this. If anyone wants to let me know. Any questions, issues with delta math? You can type in the chat, turn your mic on. Were most of you able to successfully do everything? Again, I'm going to post assignments. You're not getting a grade for this, so don't panic if you're like, oh, I didn't do it. Seems like a good chunk of people have 100% here. No issues? Okay. One thing that I saw, I think a few people wrote like they weren't sure how to type in exponents. Does anyone want to share how you could type in an exponent on delta math? Yeah, I always call this like a little caret. So when you type, let's say you want to type in x squared on your keyboard, you would hit this, and delta math automatically, recognizes it as an exponent. Or shift 6. Yep. Okay, and nothing else with delta math. We all found it. How did you guys find it? Was it enjoyable? Was it kind of annoying? Didn't really like it? Yeah. So like I said, not something that we use every day. More so like drill and practice type stuff. It doesn't work well for like word problems and like heavy graphing related things. But for this, pure algebra skill stuff, it does work well. Gives you immediate feedback, tells you if you got it right or wrong, tells you what the answer is, shows you how to do it. Sometimes their explanations are a little weird. It might differ from how I tell you how to do something. Once in a while, let's say I set it as, hey, you have to answer 10 questions. That's the other thing with Delta Math. If I set it for 10 questions, that means you have to get 10 questions correct. Think about, if your teacher gives you textbook homework and like do these 10 questions. Technically, you could just sit there and write, gibberish in your book, and not saying that people do that, but at the end of the day, you could have gotten all 10 wrong, maybe put in very little effort. Delta Math, you actually have to get them correct. So if you get it wrong, it doesn't count as anything. But once in a while, some weird examples will pop up, or like, ooh, I don't really like that. So there are some downsides to it, but I think a lot of the pros outweigh those cons. Second, supplies. Supplies, one of the major things that we talked about, obviously your basic stuff, that's going to be the same for every class. Hey, pens, pencils, folder, notebook, blah, blah. That's not what I'm really talking about. For our class, the major one is, we have a lot of questions on it, so I try to talk about it as much as I can in the summer. The TI-84. This is the model that you're probably going to see, on the shelf, or if you Google it, or if you look on Amazon. The TI-84 plus CE. Okay, they come in a variety of colors. There's new ones that come out every year, but the TI-84 plus CE is the model that we're looking for. Any TI-84 works. Someone even said like I had when I was in school the TI-83. That works. Any TI-84, the TI-84 plus, the TI-84 just as it is. It's just a little bit thicker. The plus CE is thinner. It's in color now. It's all they come in cool colors. So there's not really that much of a difference between those minor model differences, but we do want that TI-84. I told the class last week, for all you guys that were there, sometimes what will happen is your parents go shopping for it, they just see a sign that says graphing calculator, and they grab, a Casio, another off-brand one, and it unfortunately doesn't really translate to what we do. So we do want the TI-84 plus C. Not something you have to run out and get right away. A lot of you guys already mentioned that you do have it. That's great. But we want it like the first few weeks of school. I have a class set in my room, but obviously you need it at home. Homework, studying, just your own use. Okay, we'll do a little review from last week. We talked about polynomial operations, and like I said, we'll talk about polynomial factoring today. Any questions before we get started? How about we'll do a little warm up at the bottom here. So we'll say simplify, and we'll do a little multiplication problem. Okay, so in your notebook, if you want, I'll scroll down a little bit. If you want to copy down and try that problem, express in simplest form, standard form, we'll talk about that. We'll review all the vocab that we talked about last week as well, but take a few minutes to try that one out. We have x squared plus 5x minus 2 times 3x minus 4. If you have an answer and you want to type it in the chat, go ahead and do so. So we do want to multiply this out. We're not, think we might be thinking of, I'll give you a hint, box method from last week. So you'd want to draw your little grid, you'd want to multiply it out. And part of the reason why I changed the schedule a little bit with factoring today, we're going to see the relationship between factoring and really what this amounts to is multiplying, right? Factoring and multiplying are heavily related. How many people in here were able to watch the video? Maybe you didn't attend last week, you saw the video. Maybe you did attend last week and you didn't get something and you watched it. We'll go over this in just 1 minute. No, we're not factoring, you're just simplifying. So yeah, why don't we start, I guess? So I'm going to draw a little 2x3 grid. Okay, so we said the strategy for multiplying is using what we call box method. We draw a little 2x3 in this case. The 2 is for the binomial, 3x minus 4. The 3 is for the trinomial. Basically, I related this to the multiplication that you do in elementary school, right? The multiplication tables, the ones that you still find in the back of your notebook for some reason. They still put those there. I don't know why. Whereas you multiply columns and rows to figure out what goes in a given cell. Just like you're like, oh, 8 times 7 is 56, right? So to figure out what goes here, I'm saying, hey, what's 3x times x squared? So what should go in that first cell? 3x to the third. We did talk about exponent rules last week. So adding exponents is something that we talked about. Hey, x squared times x, that's really x to the first. So we're adding those together to get x to the third. A lot of you guys mentioned like, hey, we talked about this in 6th grade math. Maybe you did some exponent rule stuff. Maybe you did some box method stuff. Next cell, I'll go to the right, is going to be 5x times 3x. That would be 15x squared. Negatives are a big, an area where we can make some mistakes. People forgetting that they're there, forgetting that they exist. So 3x times negative 2 would be negative 6x. Okay, that's 3x times negative 2. Bottom row, negative 4 times x squared would be negative 4x squared. Bottom middle would be negative 20x. And bottom right would be positive 8. That's negative 4 times negative 2. Okay, now standard form. Standard form we talked about last week means everything's basically as cleaned up as it could be, and everything's as condensed as it could be. So we have like terms. So I'm going to start with the highest exponent. That's the other part, sorry for standard form. You work your way down, starting with the highest exponent in descending exponential order. So what's the highest exponent I have here? X to the third. So that's going to be my first term. Basically, your exponent is like your priority, kind of like boarding a plane. Group A, Group B, Group C. Same thing here. The higher your exponent, the more priority you have. Now for my x squareds, I do have like terms. So I have negative 4 and positive 15. If I combine those, I'll get positive 11. Okay, my x squareds do combine. For x, I have, oops, if that happens. Need to use the highlighter. For x, I have negative 6 and negative 20. Okay, combining those together, like terms, remember, have to have the same variable and the same exponent. So no, I can't just combine everything with an x here. Combining those two together, I'm going to get negative 26x. Once again, signs and things like that, important. The good news is you are always allowed to add calculators. So if you're a little uneasy with like, oh, I'm not great with my integer rules, I combine those and I put negative 14. I made a mistake adding and subtracting with negatives. You do always have your calculator for backup, for support. And last but not least, we have the constant, and that's our final answer. So 2 things. Once again, make that standard form. It's in descending exponential order. We start with the highest, we work our way down to the constant, and everything's been fully combined. There's nothing else I can condense here. So it seems like a bunch of people that wrote it in the chat got it correct. Yep, very good. Any questions with this from last week? Did you guys do box method in 6th grade math? Maybe towards the end of the year, did we do like multiply? Some people are saying yes. Miss Mavro. Camerata. Okay, awesome. Yeah, because I noticed some people put in the Google form like, hey, I did this, a little bit of review. So that's awesome. Some other vocab from last week. We called this a constant. Constant is just a name for a plain old regular number. Why is it a constant? Because it doesn't have a variable. So 8 is always going to be just 8. It's never going to change. Can anyone tell me how many terms our answer was? How many terms do you see in that box? This one's tricky. How many terms were in our final answer? 4 is correct. The best way to think about terms, I said last week, plus and minus signs act like barriers. Might be a little too wide here, but an addition and a subtraction sign separate terms. So I have a grand total of 4 terms in my final answer. Good. Can anyone tell me what the lead coefficient is? What was the lead coefficient? Just going to abbreviate it. The lead coefficient. Not 3x cubed. No, be careful how you answer this. Not 3x cubed, not x cubed. Just 3. You would just say 3. Coefficient is a number in front of a variable, so you don't want to include the variable when you say that. And in this case, the lead one is just the very first one in our final answer. So you would just say 3. Saying 3x cubed would be wrong, would be incorrect. And degree. We talked about the word degree. Not to be confused with temperature or anything in that capacity. Degree. What would be the degree here? Also 3, coincidentally. Degree is just the highest exponent. So you would just say degree 3, a third degree, something like that. The grammar doesn't matter. Degree of 3 or third degree, same thing. Degree is referring to, hey, what was the highest exponent you had? Just some random polynomial vocab. Okay. Factoring. So we'll talk about that today. I'm assuming we have some baseline with factoring. Some of you guys mentioned you did some like GCF factoring, and I know that's a 6th grade standard. So you should have done it. I don't know how far you went with it. I don't know if in May or June you went even further, but we'll get into some more algebra related factoring. So no, this isn't all we're doing today. GCF, we'll start with this. We'll talk about the relationship between multiplying and factoring, and then we'll learn some new strategies for factoring polynomials. Stuff that you should walk out of here today saying like, hey, I learned something. Let's keep it simple. I learned a new skill, right? Maybe some of you are in here like, hey, I know all this stuff, great. But I don't think you covered this in the end of 6th grade. Maybe you did. Okay, so some factoring basics. Okay. I'm going to start on the bottom of this slide. So factoring, and really what we were doing in like the warm-up, we call it multiplying, you call it distributing. Factoring and distributing are opposites. They're opposite ideas, opposite concepts, opposite processes, right? If distributing is multiplying, factoring is like breaking it back apart. When you do that 3rd, 4th grade, 5th grade, when you did like factor trees and prime factorization, right? What you were doing was you were factoring a number. Now we could factor expressions using that same idea, right? We could break it apart into pieces. You could think of factoring as splitting an expression into the product of 2 or more monomials, polynomials, terms. Another important idea with factoring is we're not changing the value of anything. We're changing the way it looks. So we're not manipulating, the value. We're just changing its appearance. Just like how you changed 10 to be 5 times 2, it was still worth 10, right? You just factored the number. We could do that with expressions as well. So up there, I could say, hey, 4 times 2x plus 3y is the same as 8x plus 12y. Just some of the basics of what factoring is. So what's the relationship between factoring and multiplying? They're opposites. Factoring is like dividing, I guess, if you want to think of it. I prefer to think of it as like breaking apart or splitting. But yeah, technically, I guess it's dividing. All right, so I know we have a little bit of a background with GCF. Like I said, something that you covered in 6th grade. So I figured we'd just kind of jump into these problems together. GCF, of course, greatest common factor. So when you factor using GCF, what you're saying is, hey, what do these terms share that I could pull out from them? Okay, that's going to be outside of my parentheses. And then inside my parentheses is going to be whatever remains. So your answer is going to look something like this. The GCF is going to be hanging out front. And then inside, you can call it remainder. If you want to be fancy or technical, you can call it quotient. Okay, our answer is going to look like that, obviously with numbers and variables in place, but we're pulling out a GCF and we're going to leave whatever remains inside the parentheses. Okay. So for the first one, what do 8y and 72 have in common? They don't share any variables. We'll get to variables and GCF stuff in a minute. GCF stuff. What do 8y and 72 have in common? Just 8. Just the number 8. So our GCF here is 8. Okay, that's going to be outside the parentheses. Remember, GCF factoring is like making it a distribution problem. If that makes sense. With distribution, you have a number in front, you draw your loops. Factoring is like a pre-distribution problem. You're bringing it back to that. So I'm halfway done. Now I have to say to myself, hey, what should I put inside of it? You could do this through actual division, like, hey, let me divide 8y by 8. Or you could say to yourself, mental math-wise, hey, 8 times what would give me 8y? I'm just missing a y. 8 times what would give me minus 72? That's just no. And that's my answer. Okay, I know this is basic. We got some more complicated ones down on the bottom, but I did want to explain this a little bit more thoroughly. If you were absent last week, one thing that I talked about that's difficult with this class sometimes, this double accelerated, this 7th grade algebra class, whatever you want to call it, we're all coming here from a different place, right? We all have different levels of understanding. So especially in these summer sessions, I'm trying to make sure that we're all, starting from a level playing field. Another nice thing here is that you could easily check your answer. How could I check to see if I did this correctly? How could I check? Selena, I'll be posting these. I'll post the PDF after our session today. So yeah, if you missed something, I'll be posting it. How could I check that I did this correctly? Just distribute. That's a really nice thing. Remember that diagram where it was like a cycle? Since they're opposites, if you distribute, you should get what you started with. Now for B, can anyone tell me what the GCF, you could say equals to, what's the GCF for B? The number 3 they share, did they share any variables? The first term has an a cubed, the second term just has an a. So what do they share variable-wise? They do share just an a. The rule with variables is this. First of all, each and every term has to have that variable. Okay, if you don't meet that condition, then forget about it. So each and every term has to have that variable. And if they do, you take the smaller exponent, because that will be the minimum that they share, or suppose the maximum that they share. So if you have an a cubed and an a, all that they share is an a. You can't say a cubed here because the second term doesn't have a cubed. Now, exponent rules do come into play here a little bit. What should go in my parentheses? 3a times what would give me 3a cubed? What should go in my parentheses? I'll give you a hint. Think about exponent rules. What could you hit 3a with to give you 3a cubed? Yes, a squared. Very nice. Reason being, 3a times a squared, you would add your a's together, or add your exponents, sorry. Remember, this is really a 1. That would give you the a to the third that you're really looking for. And how about for my second term? I need a 42a. I have a 3a already. What could I hit 3a with to give me 42a? Just 14. I don't need anything else. I already have the a. So if I put another a there, that's going to give me a squared. I don't want that. 3a times 14 gives me 42a. Very nice. And once again, I could check this just by distributing. 3a times a squared, 3a times 14, check, check. All right, example C, we don't see any numbers, or coefficients, I should say. So that's going to make it easier in one way, right? We don't have to worry about any coefficients. But we do just see variables, and we see two variables here. Can anyone tell me what the GCF is? We have xy to the 6th minus x cubed y4. xy to the 4th would be the GCF. Very nice. Think of these as like separate if you're confused, right? So take them like one piece at a time. For x, we have x and x cubed. So do they both have an x? Yes. So take the smaller one, you take x, okay? For y, do they both have a y? Yes. We have y6 and y4. We take the smaller one, y4. Why do we take the smaller one when I phrase it that way? Because again, that's what they'll share as a maximum in common. If one of them has a y to the 6th and the other one has a y to the 4th, the most they have in common is y to the 4th. You take the smaller exponent, if they both have it. And now, in our parentheses, what's left behind? We're going to put a y squared here. I don't need any x's in the first term. Y squared, because y to the 4th times y squared gives me y to the 6th. My second term would just be x squared. Okay, that's going to give me x squared times x gives me x cubed, and I don't need any y's. We're going to talk about a strategy later today that you could take this example a little bit further, but for now, we'll leave it like that. And why don't we try this? I'll give you guys a minute. We have our first trinomial. The first three were all binomials, but same idea applies. See if you could factor example D using GCF. So you should have something in front of the parentheses, and then 3 terms now, instead of 2, 3 terms inside the parentheses. Take a minute for example D. Copy and try. All right. Anyone want to share in the comments what they got? Okay, let's see. So with three terms, the same rule applies. They all have to have it. So numerically or coefficient-wise, we have a 2, 4, and an 8. That would just be a 2. And now variable-wise, once again, they all have to have it. Do they all have a y? Yes. We take the smallest one. That would be y cubed. Again, we take the smallest one because that's what they at least all have. And now inside of it, we could do one of two things. You could actually divide each term by that GCF if you prefer division. Or you could say to yourself, kind of like mock multiplication. Hey, what times that would give me that first term? What times that GCF would give me the second term? So first, we don't need any coefficients. We're just going to put y to the fourth, because y4, y3 would give me y7. My second term would be 2y squared. Okay, 2 times 2 gives me 4. Y squared times y cubed gives me y to the fifth. And last, don't forget the sign, minus, because of this, 4, just minus 4. No y there because we already have a y cubed. Looks like the comments were all good. So excellent. Questions with GCF factoring. This was the most relatable because obviously you did a little bit of this, this year. I'm not sure to what extent, maybe more so examples like A or B. I don't know how complicated we got, but GCF factoring does come up in algebra. So while this is, review, it does come up. Obviously, we spice things up a little bit. It gets a little bit tougher, but GCF factoring, our first strategy or technique. We're going to cover probably 2 or 3 more today. And then you'll see they're all kind of interrelated. Like GCF factoring can help us with a more complicated example later on. Something that you learn in 6th grade can end up helping you with a more complicated, like high school example. Questions with this before we move on? No? Okay. Our next strategy is going to be for trinomials specifically. So this strategy only does work for trinomials. Trinomials referring to 3-termed expressions that look like this. Okay, I'm looking right here if you see the little laser dot. Excuse me. So x squared plus bx plus c. So what that means or what that refers to is like a trinomial where there's actually numbers there. So you see an example, maybe that's, will make a little bit more sense. B and C are just standing for some unknown number, some generic number, right? Will be there. X squared plus 10x plus 9. Okay, so it has to have a squared variable to start, and then some number x, and then some constant on the end. We call this rule very creatively named. I just call it sum product rule, sum product. So it's kind of like a puzzle for people that like puzzles. It's not a very exciting one, but it's a puzzle in the sense that you're trying to find something. You're trying to find 2 numbers that have a sum, that means they add up to, a sum of B and a product of C. Product means you multiply to, right? And you might be saying, what are you talking about? So let's make up a different example here. Let's say, let's do an easy one to start. Okay. So we have x squared plus 7x plus 12. So in this case, the sum that I'm looking for, the sum is always going to be the coefficient of that middle term. So the sum that I'm looking for is 7. Okay. The product that I'm looking for is going to be the constant on the end, just the number 12. So this is what I mean with it's almost like a puzzle, right? You're saying to yourself, hey, what 2 numbers add up to 7, but at the same time they multiply to 12? For example, let's say I were to guess 6 and 2. 6 times 2 is 12, right? But is 6 plus 2 7? No. So we got some work to do. 12 and 1 multiply to 12, but do they add up to 7? No. And also signs will become a part of this. Negatives get involved, right? I tried to choose an easy one as this first example. Does anyone know what the two numbers are here? 3 and 4. Once you find your two numbers, watch what I do. Run out of space. This is it. And if you notice, it looks like a box method example, like the beginning of a box method problem. You're just going to put the numbers in those two. I call these bubbles sometimes, little binomial parentheses. I'll call them bubbles. Not a very technical term. But you're just going to put x plus whatever your first number was, and then x plus whatever your second number was. Okay? And now how could we check this if we really wanted to? We could make our little 2 by 2 box, multiply it out, and we should get, and we would, x squared plus 7x plus 12. So when you're done finding your two numbers, whatever the variable is, it's not always going to be x. X is the most common. A, B, Y, whatever it is. Your bubbles are going to look like this. If you want to do this in the beginning, and then whatever numbers you find, go there. Okay. This little chart, if you're like, well, why do, what was the purpose of that? It's helpful in the sense that, just moving that out of the way, just helps you see things. Sometimes it's referred to as like a diamond, a little X. Just helps you, I don't know, for visual learners, see that there's two things going on here at the same time. So, hey, 3 times 4 gives me 12, and 3 plus 4 has to give me 7. So if we try the example down there, we're looking for two numbers that add up to 8 and that multiply to negative 105. This one's going to be a little trickier. I'll go over some helpful tips to help out with examples like this. First, what if it isn't given in this format? Then other strategies exist, or it just might not be factorable. Yeah, this only works for, these are very, very common. These trinomials are your more common factoring examples. Notice that we have a negative product here. What's the only way that you can get a negative when you're multiplying? If you're multiplying two numbers, what's the only way that you could get a negative?
You cannot multiply a number by...
My Apple Watch thought I was asking the question. Yeah, the only way to get a negative is if you have one of each, right? A positive and a negative. So that's going to help me a little bit. Okay. The other thing to consider when you're searching for two numbers, there's much fewer options for the product than there is for the sum. What do I mean by that? There's a lot of things that add up to 8, right? Especially when you mix in negatives. I could sit here forever and come up with examples, right? 10 and negative 2, 11 and negative 3, 12 and negative 4, 6 and 2, 5 and 3, 4 and 4. I could sit and just keep doing that forever. There's not many examples for products, right? Things only have a limited number of factors. So it's much easier to start looking down here and then to use the sum almost as like the secondary check. Does that make sense? So instead, think to yourself first, hey, what multiplies to 105? And it is going to be a little bit of a guess and check. You're not going to get it right away. So 105, in my head, I'm saying, all right, I know at least one number that goes in there. I know 5 goes in 21 times. Okay, that's not going to work. 21 and 5 isn't going to get me to 8 at all. And then you do want to make sure your signs check out. Sometimes you might have your signs backwards. So what do we think here? Does anyone find the two numbers? 15 and negative 7. Very good. Let's make a mistake for a moment. Don't copy this. Let's say you did this. This is very common, especially when you start factoring early on. 15 times, negative 15 times 7 is negative 105. However, if you add these together, do they add to positive 8? No, they add to negative 8. So we were really close. If that ever happens, just flip your two signs. So if you get really close and you're like, oh man, I thought I had it, just flip them. Now we have to put it all together. You wouldn't just circle your little chart. What is the actual factored form of this? Remember I said earlier, make your two little bubbles. Bubbles, I'm just saying spaced out parentheses. We put X in each one. If we think about box method, that would give me X times X gives me X squared. Now I'm going to put the two numbers we just found. It does not matter which one you put first. Why does it not matter? Commutative property, order doesn't matter for how we multiply. So I'm going to put 15, and then I'm going to put minus 7. Does it matter if you wrote your bubbles the other way? No. And that's my answer. And like I said earlier, you could check, you can make a little 2x2 grid. Obviously, you know, that's going to take a little bit of time, so you certainly don't need to do that, but it can't hurt. X plus 15, X minus 7. Questions with this skill or strategy? I know this one should be new. How many people were aware of this before this slide? How many people know how to do this? You've seen this? A few people say. Okay, cool. So we'll practice with this a little bit. Takes a little getting used to. You also don't need to write the word sum and product. If you're doing like your own example, you could just make like an X. You could do something like this. Okay, I believe I have practice problems here. Yeah. So I'm going to zoom in because it just says like, so the instructions for this, it will usually say factor, or in this case, it says express as a product of two binomials. That's another way of saying like factor. So I'm going to zoom in on the two problems. If you want to copy them down, as a hint, your answer should look like this. So double bubble, double bubble. Obviously, someone was asking like, what if they don't look like this? Factoring problems are specific because they have to be factorable. It wouldn't make sense for me to give you an example that like didn't work out. In other words, like, why would I ask you to factor it if it doesn't factor? So keep that in mind. Copy those two down, try it out. You can make your little X or diamond, your sum and your product. There's not a lot of work for these, right? Double check that your numbers do work out. Sometimes you get like a false positive. It seems like it's going to work out, but it just doesn't. People that know how to do this, did you guys do this in class? Did you just outside of school? Just write it in the chat. If you're confused, I'll start filling this in. So your sum was 9, Your product is negative 52. The bottom one, you always want to pay close attention to your signs. Does anyone find the numbers for the first one? Remember, you want to start with your products. Very important trick. It's not really a trick. We said there's a million things, there's an infinite number of things that add up to 9. Considering that you could mix in negatives, right? There's very few products for 52. It is going to be 13 and negative 4. Very nice. If you thought it was 4 and negative 13, those would add up to negative 9. So I said if that ever happens, just switch the two. If you're like, oh man, I was so close, just switch them. That should fix it. And now your bubbles would be x plus 13, x minus 4. Very nice. Very nice. And for the next one, we have a negative product. So once again, that tells us one of each. If you have a positive product, it doesn't necessarily mean the two numbers are positive, because remember, they could also be two negatives. So you'd have to check the sum in that case. For the second one, what numbers did we get? Negative 20 and positive 3. Very good. Negative 20 plus 3 gives us negative 60. Negative 20 plus 3 gives us negative 17. Negative 20 times 3 gives us negative 60. Very nice. Once again, especially early on, if you wanted to check it, you can multiply it out. I'll just quickly do the first one, x squared. You could draw your little 2x2 grid. 13x. We have negative 4x. We have negative 52. Remember, we said very early on, factoring is not changing anything. It's just changing the way it looks. So notice I'm able to come up with the original problem. That should always be the case with factoring. We're not changing anything. We're changing its appearance. Questions with this strategy? I just call this sum product, trinomial factoring, sum product, trinomial. Questions with this one? We still doing okay? All right. I'm going to skip this. There's just some extra practice with factoring, but I feel like we're doing okay. We can go back to that later. Should we? Let's do this. We'll take a little mini break here as well. We'll try these 3 problems. Notice this is what I was saying earlier. They're not always going to be x. Like the first one says y squared. Does that change anything? No. But when you're doing your double bubble, just make sure you say y instead of x. We'll try these 3. What we'll do is we'll take, it's 9:52. We'll take like 3 or 4 minutes. So if you need to use the restroom, if you want to grab a drink, take a little bit of a break here. And when we come back, we'll go over these 3. We'll say 9:56. We'll hop back on and go over it. I figured we'll take a break here rather than starting a new skill and taking a break. So after this, we'll go over, we're going to cover 2 more strategies, hopefully, if we have time. Difference of 2 squares, what I call dots, and a related strategy to this one. There's another trinomial strategy that works out when it doesn't look like this. Someone asked that earlier. Okay, so try these 3 problems. If you need to take a break, feel free to go ahead and do so. And when we come back, we'll take a look at the answers. All right. What I'll do is this, give me a little bit more time. I'm just going to set up my bubbles for each one. The other reason why it's called sum product, just the order is important, obviously. So that first number is your sum, the second one is the product. You don't want to switch the two. Did we find it for A? What two numbers add up to 30 and multiply to negative 64? Negative product, so I want one of each right away. 32 and negative 2, very nice. The 32 minus 2 gives me 30. 32 times negative 2 gives me negative 64. Next one, once again, one of each side. We have a lot of negative products. Just coincidentally. What adds up to 8 and multiplies to negative 65? 65 doesn't have very many factors. 13 and negative 5, very nice. Now, if you're someone that you feel like you struggle a little bit with factoring, there are some calculator strategies, right? Just simply using your calculator to test it out, to divide by 5, to divide by, hey, does this go in? Does this go in? And there's some other things we could do as well that I'll show you probably in class when we talk about this topic again. So don't panic if you feel like you struggle with the number sense part of this. Like, hey man, I'm just not, it takes me a while to think about what factors, what numbers go into 65. That's okay. And it's a skill. As you do more and more of these, you get used to them and you get a little bit better at it, like anything. All right, and the last one. It's good we're doing an example like this. Take a look. We have a positive product. Now, that does not mean that we have two positive numbers. The reason being, we have a negative sum. So if we have a positive product, that tells us that the signs are the same. It's either plus plus or negative negative, right? Two negatives make a positive when you multiply. So how do we know which case it is? Being that we have a negative sum, how could it be two positive numbers? That wouldn't make any sense, right? So we know that they're both going to be negative. Two negatives multiplied gives you a positive, and two negatives added together are still going to be negative, right? What are the numbers here? 12 and 6, very good. Negative 12 and negative 6. Excellent if you're able to get these. If not, at least you try. Maybe you thought you got it correct. Maybe you had your signs flipped. Maybe you put negative 13 and positive 5 for the second one. But as long as you were close and you gave it an effort, that's all that matters. You're learning something today. Okay, questions with this before we move on to dots? All right, let's start dots. Dots is going to be a fun one. So dots is an acronym. This to the bottom. DOT stands for difference of two squares. Sometimes teachers or textbooks will call this something related to that, but like DOS or I don't know, I've heard a few different things, but I like DOTS. It stands for literally each letter, difference of two squares. So this strategy only works for binomials. That's the two. Binomial, two terms. Okay, perfect squares are going to be talked about a lot. So being comfortable, being able to recognize your perfect square is very important. Perfect squares, 1, 4, 9. Right, I think we could all recognize these if we saw them. Up to a certain point, right? But the more comfortable you are with those, the better you're going to be with this strategy. Perfect squares are involved. Subtraction, okay, that's the D in dots. So this does only work for a difference. If there's a sum, if there's a plus sign, this strategy does not work. So the first letter of dot, difference, means that this only works for subtraction problems. Does not work for addition problems. Difference of two squares. So it's a difference, it's two terms. The O in dots isn't really important. It's a difference, it's two terms, and it's squares, meaning everything is a perfect square. What is a perfect square? 9 is a perfect square because it's 3 times 3. What makes a variable perfect? Very easy. They just have to have an even exponent. So variables are considered perfect when they have even exponents. For example, just like how we say 9 is perfect because we can write it as 3 times 3, x squared is perfect because we could write it as x times x, right? A perfect square means you could write it as a product of basically the same thing twice, right? Something repeated. So if it's even, you could do that. You could just chop it in half. X to the fourth is x squared times x squared. X to the sixth is x cubed times x cubed. So if you're a variable, all you need to have is an even exponent. You don't necessarily need a perfect square exponent, just an even one. Okay, now to factor a difference of two squares, you're going to create two bubbles once again. You're going to create a bubble with a plus sign and one with a minus sign right away. Doesn't matter the order if you flip it. Okay, we'll talk about why you do that. You're going to take the square root of the first term, that goes first. You're going to take the square root of the second term, that goes second. That's it. Okay, so we'll try, I think it will make a little bit more sense if we try an example with this. So let's look on the right. We're going to factor 16x to the fourth minus 49. First of all, the number one thing with this strategy is, why is it a dots problem? What makes this a dots problem, right? So let's go through that. Because that's the hardest part. Like, is this a dots? Can we use this skill or strategy or not? What makes it a dots problem? Is it a difference? Do we have subtraction? Yes. Do we have two terms? Yes. Is everything a perfect square? 16 and 49 are perfect, so yeah. Is our variable have an even exponent? Yes. So this is a dots problem. We could use this skill, this strategy. So I'm going to double bubble. Okay, fill my two parentheses. And I'm going to put a plus and minus, and we'll go back to that later on, maybe when we're checking why we do that. Now what you're going to do is take the square root of the first term. Basically, what you're saying is, what times itself would give you 16x to the fourth? You can split it up. So what times itself would give you 16? 4, right? That's going to be the first term in each bubble. What times itself would give you x to the fourth? For variables, you could just simply cut them in half. So what times itself would give you x to the fourth? X squared. Chop the variable in half. Chop the exponent in half, I should say. Okay? Everything that you write inside the bubbles is going to be a mirror image, aside from the plus and minus. So you should be writing the same thing twice, aside from the plus minus. Now for the second term, this one's a little bit easier. What times itself is 49? Don't say 24 and a half. What times itself is 49? 7. And that's it. Again, you take the square root of the first term, take the square root of the second term, and put them in your bubbles. Your bubbles are identical except for the plus minus. And that's dots. Now, our first step was to make two bubbles, put plus minus right away. I put this as a first step because we don't want to forget to do it. But why do we do that? Why do we put a plus and a minus? That seems kind of weird, right? Pen's a little too thin. Why do we do that? Because if we were to multiply this out, oops. If we were to multiply this out using box method, so I'll draw a little 2x2 grid. Something happens when we put differing signs. Does anyone know what happens? That's part of it. He's saying we wouldn't get the correct sign, right? But something happens with that middle term, because usually when we do a 2 by 2, we get a trinomial. Why do we not get a trinomial here? They cancel. Your middle term cancels out. If you do any other 2 by 2, right, you get a trinomial answer. You get your first term, you get like 2 like terms in the middle, and then some constant on the end. But if you put the exact same thing in each bubble, but differing signs, that middle term will cancel out, giving you a binomial answer. So by putting different signs, we're canceling out that middle junk, whatever it may be. Yep. And why I like to do that right away, like I said, just so we don't forget. So right away, double bubble, put a plus minus. Questions with, I'll zoom out, questions with this strategy for dots. The toughest part about it is going to be recognizing when you can use it. I always say when we're learning a skill or strategy, like, excuse me, it's easy like when we're doing it, right? Like in a moment, I'm going to say, hey guys, use dots, try these 2 problems. But when it's tough is a few days removed from it, a week removed, 2 weeks removed on a test where you're like, wait, is this dots or is it something else? So that's where it's important that we really understand it. Obviously, you know the day that you're doing that lesson, hey, it's everything we do is going to be dots. Everything we do is going to be this strategy. But to really understand it is, hey, could you recognize it removed from this lesson? Could you recognize this in the wild on its own? Questions with this before I move on? We're going to practice with it, but questions before I move on to the next slide. You don't actually need to take the square root, more so like mental math in your head saying like, hey, what times this gives me, what times itself gives me this? Like I said, for variables, chop them in half. All right, why don't we try these 2? I don't know why these are numbered 3 and 4, ignore that, but copy 9x to the 6th minus 36y squared, and also 25y minus 64. Keep in mind your answer should be double bubble. Double bubble meaning 2 spaced out parentheses. Double bubble right away if you want to. Put a plus minus in each one so you don't forget. Question? If you want, you can type your answers in the chat. I know it might be a little annoying. All right, let's try these 2 out. So for the first one, we have 9x to the 6th minus 36y squared. So obviously we know it is, but let's just review. Why is this a dots problem? We have two terms. We have a difference. Is everything a perfect square? 9 is, 36 is. Do we have even exponents? Yes. So now I like to do this right in the beginning, just so we don't forget. Now we're taking square roots. What times itself is 9? 3. 3 times 3 is 9. For variables, don't overthink it. You could chop it in half. The reason why chopping it in half works is when we multiply x cubed times x cubed, we add it together. So you're really breaking it up into two equal groups. That's why I said chop it in half. X to the 6 becomes x cubed, x cubed. For my second term, I'm going to say 6. 6 times 6 is 36. And for y, just y squared, it's just going to become y. Okay, that's factoring using dots. Now we do have a GCF here. We could break it down further, but for our purposes, we'll just leave it like that. We could pull out a 3 from each of these if we really wanted to. For our second one, once again, we have a difference. We have perfect squares. We have an even exponent. Good, good, good. Checks off all the boxes, right? My double bubbles, I put plus minus. And what times itself is 25? 5. What times itself is y to the 8th? Y to the 4th. Again, chop it in half. And 64 is just going to be 8. Plus 8 minus 8. That's it. That's dots. Like I said, once you recognize it, this is one of the easier strategies, but recognizing it out of context could be difficult sometimes. Questions with dots? The next slide we're going to try, let's see, do I have it? Okay, yeah. So is going over what I was mentioning earlier. The difficult part about this is like, can I use dots or not? Is actually using dots that difficult? Not really. There's nothing really that crazy once you know that you can do it. It's just a matter of some arithmetic, right? Like, hey, what's the square root of 16? So for each of these, what we're going to go through these together. What we're going to say, we'll treat it as like yes or no, true or false. Well, we'll say yes or no. So for each one, we're going to say if we think it's a dots problem or not. We'll do them one at a time, so don't skip ahead here. So we'll say yes if we think it's a problem that, hey, we could do dots to this, we could use dots, or no if we think we can't use dots. Not if it's factorable or not. Like, hey, there's something else you could do. Just straight up, can you use dots for this example? So for A, you could use the chat. Let's say yes or no. Yes if you think it's a dots problem, no if you think it's not a dots problem. This is not a dots problem. Kind of looks like it. It's kind of close. Can anyone tell me what's wrong with it? Why is this not a dots problem? It's the 50, yeah. If that 50 was something else, a perfect square, it would be good. There's a GCF here that you could do, but still no dots. The 50 is what messes it up. How about for the second one? Second one, we have 81A12 minus 144. Yes, this one is good. Big numbers, but everything's perfect. 81 is perfect. A12 just has to be even. 12 doesn't have to be perfect square. And 144 is a perfect square as well. That's 12 squared. So yes, that is good. B is good. How about for C? Is C a dots problem? Ooh, be careful. So a lot of people say yes. C is not a dots problem. C is no good. You might have missed it. Why is C no good? I think everyone just hopped on yes right away. What's the first letter in dots stand for again? Difference. Is C a difference? No, it's a sum. It's not called SOTS. There is no sum. There is a sum formula for like other complicated things, but for difference of two squares, no. This is not a difference of two squares. It fails the first check, right? There's really three checks. Is it a difference? Is it two terms? And is it perfect squares or squares? This is not a difference, so no. So it tricked you there a little bit, yeah. It looked, otherwise, was it perfect? If I change that plus sign to a minus sign, is it perfect? Yeah, it was good. And how about for D? What do you guys think for D? All right. So I was a little evil here. D, believe it or not, is a dots problem. You might be saying, what are you talking about? 20 is not perfect. X to the fifth isn't perfect. D is a dots problem. That was really tricky because watch what I'm talking about. Sometimes a dots problem can be hiding inside of a problem that doesn't look like it's dots. There is a dots problem hiding in here. I promise. Using what we learned earlier this morning, what could we do to this? We could do GCF, right? If I pull out a GCF of 5 goes into 20 and 45. And they also have a GCF of X. So I'm pulling out a 5X from each of these. Watch what's left behind. If I pull out a 5X from 20x5, what's left behind is 4X to the fourth. And if I pull out a 5X from 45X, I'm left with minus 9. And what do you guys think about now? Does this meet the condition of dots now? Yes, that's what I was saying. Very sneaky, obviously. Just a good teaching moment to say, like, hey, sometimes things are hiding in plain sight. And now we could do dots. And one strategy that we are going to learn later on this year, this is called factoring completely. Sometimes you may need to use a combination of strategies. You may have to do GCF and then dots. Maybe you have to do GCF and some product like we did earlier. In other words, it's like a compound problem. I always throw this question in and no one ever recognizes it, so. Don't worry, they got D wrong. So technically it was. Okay, questions with dots. We have around 10 minutes, which I'm going to attempt to start our last one. And I'm saying attempt because it is the more involved of the bunch, but let's try it out. We're good with dots? Okay. Where do I want to start here? Let's do this. I'll zoom in with this. So our last strategy that we're going to learn has to do with trinomials again. So we're going back to trinomials. What do you notice is different with this one? What's different than this one than the other ones we saw before dots? We call that sum product. What's different about this example? What's different is the fact that there's a number right here. Yeah, this messes things up a lot, believe it or not. Because now, you know how when we did sum products earlier, we were just like, oh, put an X and an X and search for your two numbers. Now, one, I don't know if it's going to be like 6X and X. It could also be 3X and 2X. And then all of a sudden it matters where the other numbers go. What I mean, like when we were just putting X and X, we said, oh, it doesn't matter. It's the same thing. Now all of a sudden it does matter. Is it 7 and 1? Is it 1 and 7? Is it some other weird combination, right? So now this unfortunately opens up Pandora's box a little bit, making our lives a little bit more difficult. However, we do have other strategies and skills to help us with this. We don't just do guess and check. You could guess and check your way through this, right? Like, let me try this out. Let me try this and box it out. But we do have an algebraic way of working our way through it. Okay, so this would be the answer for that one. I'm going to jump right into the skill, like I said, just to save some time. If you're a note person, I do have some notes on the side. Notice what step 1 is. Step 1, this is going to be important while factoring. Like, if there's a GCF, you want to make your life easier, pull it out. At the very least, it's going to make the numbers smaller. So if you have a problem with the GCF, pull it out right away. Do we have a GCF here with 5x squared plus 11x plus 2? No GCF. So we did check if there's a GCF. Sometimes there is, sometimes there's not. Step 2 is going to say multiply A by C. And you might be saying, what is that? Well, we talk about this is really a quadratic. A, B, and C are just the coefficients in that order. So we're going to multiply those two numbers together. So in this case, 5 times 2. Okay, that gives us 10. Now we're going to do our sum product that we usually do. But instead of the product being the number 2, the product is going to be 10. Again, that comes from the fact that I had to multiply those two together. The good news is you would catch yourself if you made a mistake. If you're like, oh, let me use 11 and 2. Why am I saying that? Because there's nothing that works out. So you do have to multiply here. We multiply A times C, that's where I got 10 from. Now we're going to find the two numbers just like we would normally do. What two numbers add up to 11 and multiply to 10? 10 and 1. Okay? I'm then going to do this. We're not done. With sum product, we were done at that step, right? We'd be like, oh, x plus 10, x plus 1. We're not done. So we're all the way up to step 4 already. We're now going to rewrite this. Okay? So all I did was I broke up 11 to be 10 plus 1. And you might be saying, what was the point of that? I thought we're supposed to, like, you didn't really accomplish much. But now we're going to be able to use a factoring by grouping strategy to basically split this problem in half. And doing this, just imagine that that was there, right? You don't literally have to draw a split down the middle. But on the left-hand side, if you factor 5x squared plus 10x, you could factor out a 5x. That leaves x plus 2 behind. I'm using GCF here. On the right, we have 1x plus 2. There's no GCF there. Just put a 1. That leaves x plus 2 behind. Okay? And now your final answer, if you did this correctly, this should happen. The bubble should be the exact same. So in your final answer, it's going to be x plus 2. I'm going to call that the common bubble. And then whatever is left behind, whatever is left over, goes in your second bubble. 5x plus 1 is going to go in that second bubble. These are my leftovers. So I have a common bubble and a leftover bubble. And that's it. Like I said, this one is a little bit more complicated. There's another way of thinking about it as well that I'll talk about. Just to recap, we check to see if there is a GCF. We multiply A times C to give us a new product instead of just using 2 here. We find our numbers like we usually do, but instead of being done, now we use it to rewrite the middle term. So you can't just make up how you want to rewrite the middle term. If you're like, oh, couldn't I just have started this problem and said like 8x plus 3x? No. So you did have to do those steps before because it works out a certain way where, notice what happened, the bubble was the same. If your bubble is not the same, you messed up. That's a good stopping point. Like, ooh, I made a mistake somewhere. See how I had x plus 2 on the left and right? I know I did it correctly. I have a common bubble. Hey, that's what they share in common. So I'm kind of like pulling that out from each of them. And then the leftovers, like what was in front of the parentheses, go in a second bubble. I had a 5x and I had a +1, so I just put +1. Your answer still should be 2 binomials. So we get x plus 2 times 5x plus 1. All right. I know this skill definitely is a little bit more involved. It's probably the more difficult of the skills that we've talked about. I'm trying to think. I might upload. I don't want to go over time. So what I might do is upload. I could see if I have a YouTube video on factoring. This is called factoring a greater than 1. I also have another related strategy to this called trash. Not a very fun sounding name, trash method, but I'll explain how trash works. People tend to enjoy that a little bit more. And we'll be posting Delta Math again. We'll talk about equations and inequalities next week, so we'll stop polynomials for now. Just to recap what you did today, we talked about GCF, we talked about sum product, and we talked about dots, difference of 2 squares, and then we talked about, I call that a greater than 1, meaning there's like a different number in front. So we covered basically all the factoring strategies in this hour-and-a-half session. We got a lot done. Obviously, that last one we need a little bit more practice with. I know we're a little bit squeezed with time, but I'll post some videos. I'll post some helpful resources to help out with that. Delta Math will be posted if you want to practice any and all of these skills. Any questions from you guys? How many people were able to follow along that last skill? I know that one takes a little bit of time. I said that for most of them, but that one's definitely the hardest one, I'll admit. 4 is probably your toughest. So what we'll do is maybe the beginning of next week, we'll go over some practice with that. Like I said, I'll upload some resources as well. I'm going to stop the recording.